Hi, I'm Shalini Chikara, and with me here is Dave Graff. We are scientists at MagLab and are presenting one of our most popular and electrifying demonstrations. The Tesla coil is not only visually stunning, like something out of an old Frankenstein movie, it also involves interesting science and engineering principles. The Tesla coil is basically a resonant transformer with two tuned LC circuits. The L in these circuits is inductance, basically a coil of copper wire. C is the capacitor, a device that stores energy. The frequency where each circuit works is determined by inductance and the capacitor. When both circuits have the same operating or resonant frequency, it is easier to transfer energy between them. The resonant frequency of this Tesla coil is about 200 kilohertz or 200,000 times a second. In our Tesla coil, the primary coil has 10 turns, while the secondary coil has 1200. This is the transformer part of the Tesla coil. It takes 2000 volts and steps it up 125 times to 250,000 volts. For comparison, a car battery is about 12 volts. The big ring at the top of the secondary coil is called a toroid. It forms one terminal, while the ground serves as the other terminal. That's where those 250,000 volts go, creating an electrical field so powerful it ionizes and lights up in the air. If that sounds familiar, it should. When you see a lightning bolt, that is the high voltage from the lightning bolt ionizing the air and creating a plasma of molecules where the electrons have been stripped away. The key difference is that lightning during bad weather is direct current, or DC, and the arc happens only once. Our lightning is happening thousands of times per second because it comes from an alternating current circuit, AC. But the Tesla coil cannot compare to the hundreds of millions of volts in lightning. The electric field created by the Tesla coil here is strong enough to survive to quite long distances. You can see the signal from the antenna on the computer screen and how it becomes weaker but still survives to distances far away from the Tesla coil. The electric field is strong enough to light up a fluorescent tube without any wires attached to it. Look what happens to the gas inside this light bulb. The higher the frequency, the more the current tends to travel over the surface of conductors, and because of that,